Why can't we never accelerate any object to the speed of light? I mean, we can go very close, but we can never reach the speed of light. Why is that? One of the most common explanations I got is if you plot kinetic energy versus the speed of light, you'll see that it would take an infinite amount of energy to reach the speed of light. And we don't know what infinite energy means. But my problem is that this is not an explanation. This is just a graph and this is theory. But I want to know really how we cannot reach the speed of light. And one more explanation I got was that the mass would reach infinity. Even that does not have any evidence. So, what's really happening? What is it that is physically stopping that object from reaching the speed of light? So, in this video, I'll try to explain the very same thing. So, get ready for it and let's begin. So, Einstein says, imagine you're inside a very fast moving spaceship, and inside that spaceship, there's a photon clock. Einstein, come on. How can I imagine a photon clock? Give me something real like a watch or a clock, a real clock. But Einstein says, buddy, some patience. If you understand this photon clock, the rest of the things will be understood very easily. So let's give it a try. Let's trust Einstein. So, what's a photon clock? In simple terms, there are two mirrors between which there's a photon that bounces. So, to understand, let's say it makes a tick sound when it bounces on the bottom mirror. Tick, 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 so on and so forth. So, now Einstein asks, what would the same clock look like if you see the whole thing from outside the ship? I mean, the clock would look the same to me, but there's a catch in this. If you look carefully, the photon would now be traveling a diagonal path, which means it is now going to travel a longer distance. But remember, the photon always travels at the speed of light. And now that means the photon is now going to take a longer time between the ticks. In other words, the photon clock is ticking slower, which means the clock has slowed down. And for comparison, here's how it would happen. So, illustration one, if you're inside the spaceship, tick, tick, tick. And if you're seeing it from outside, tick, tick, tick. So you can see that the photon clock has really become slower. So now what would happen if the spaceship is moving even faster? The photon will take an even longer path. And as you can see, the ticks will become even slower. So this shows the clocks do slow down when they're moving. And at this point, I'd say photon clocks do move slower. But what about a real clock? What if you place a real clock inside that spaceship? Well, Einstein says if you look at a real clock and zoom into the second hand of that clock, what would the animation look like at the atomic scale? I'd say the second hand would move like this, right? But Einstein says that cannot happen. The reason is when this particular atom accelerates, all the other atoms do not accelerate at the same time. We should know that information takes time to travel. See, atoms are bonded electromagnetically, and when one atom accelerates, we need to wait for the electromagnetic wave to travel from that atom to the other atom. And only then the information would have passed to the next atom, and the next atom would move. And an electromagnetic wave is nothing but a photon. So, a better way to think about this is like this: when this atom accelerates, it sends a photon to the other atom, then the other atom accelerates, and then the next one, and then the next one, and so on and so forth. So you can see that the whole second hand is not moving instantaneously. There is a time delay, but that is happening so fast that it feels as instantaneous. And now the real game changer question. Einstein asks me, Pawan, what if this clock is moving inside a spaceship? And wait a second, this is again similar to a photon clock, which means the photons would again take a diagonal path while reaching from one atom to the other. And that's how the atoms would move slower and the second hand moves slower. So let's look at it. The photon has not become slower, but the transfer of the photon has become slower when the ship is moving or when the clock is moving compared to when the clock is static. And therefore, the real clocks actually do slow down when they are moving. Crazy, right? And now my question to Einstein. Einstein, this is all theory, right? You proved it theoretically, but I want evidence. Does this really happen physically? Who has seen it?